In this video, we're going to talk about these two different operations of on-demand paging, and memory swapping. So the very first question to answer is, why not just simply leave all the pages, all the in-memory data on disk? Why not? This is simply because the different storage at different storage. So if you take a look at the storage hierarchy, at different storage level, it exhibits different performance trade-off, right? So main memory is somewhere over here. So which is two levels above the secondary storage, for example, magnetic disk or hard disk drive. Okay, so secondary storage, persistent storage, and the main memory is volatile. So it is significantly faster than secondary storage, for example, hard disk drive. The examples that the disk in those examples that we've been looking at. Okay, so typically the main memory exhibit hundreds of nanoseconds in terms of latencies, whereas secondary storage, for example, hard disk drive, it typically requires like tens of milliseconds. As you can see, this is multiple orders of magnitude difference. Okay, it's a huge difference. So this explains why we don't want to leave everything onto disk, because it impacts performance badly. It basically has to do with the significant performance gap between the main memory and disk. So as I've already mentioned in the previous slide, the latency it takes operating system to get access to fetch a 4-byte integer from main memory versus to fetch this 4-byte integer from disk. So by the way, to fetch this 4-byte integer from disk, you basically cannot just fetch the 4-byte as is. You have to fetch the whole data block, the whole disk block, which contains this 4-byte integer. And the typical disk block size is, let's say, bytes or 4 KB. Okay, so the DRAM exhibit like 100 nanoseconds, whereas the disk latency is for the small random data, for the small random I/O, it's typically tens of milliseconds. Okay, which is huge performance gap. So why we still want to do something beyond this physical memory? Because this is essentially how the operating system supports the so-called virtual memory concept. Why it's called virtual memory? Because, partially because it only uses main memory, the main physical memory, as a subpart, as a part of it. And because virtual memory could virtually support way much larger virtual capacity than the physical capacity of a physical memory. And the idea that back this up is the operating system to use the disk space as some sort of extension that extends the capacity of the physical memory. Okay, so that it virtually enlarges the physical memory. And this is a useful idea in the old days when the physical memory capacity is significantly limited. For example, we're talking about 64 megabytes in the late 90s. So this is too small, okay? But how to enlarge it is by using disk. And that is why the old operating system like Windows 95, Windows 98, it was extremely slow, because for whatever memory intensive applications, it is just keep doing, the operating system is keep doing IOs, because it keeps doing like swapping in, swapping out, these kind of operations, so that the application just freezes there unpredictably. Okay, and there are two ways of doing this interaction between the memory and disk. The first approach is what is called demand paging, and the second approach is called memory swapping. So let's first take a look at demand paging. So what is demand paging? Demand paging is to bring a page into the memory only on demand, in an on-demand fashion. Or in other words, only when it's being needed, okay? So the benefit of it is obvious, right? First of all, it incurs less IOs. The less IOs, the better performance it gets. And the second benefit is it requires, less memory capacity, because for those rarely used pages, those rarely used runtime libraries, you don't have to bring it into memory in the first place, but pretty much in an on-demand fashion. Whenever it's being needed, bring it into the memory. Okay, and another benefit is the better performance, faster response, basically improve the interactivity. Okay, so how to keep track of where the page is by using the reference bit or the present bit. If not in memory, if the present bit is 0, in order to get access, you need to first fetch the page from the disk into the memory. So this is demand paging. And the next approach of supporting this memory and disk interaction is what is called memory swapping. So swapping is essentially, it's kind of like the opposite operation with respect to the demand paging. Swapping basically allows the operating system to support this fundamental concept of memory virtualization, where it creates this illusion of a large virtual memory, which is effective of supporting multi-programming, so that the multi-programs can run at the same time, right, at once. And it improves better resource utilization, and at the same time, it creates this memory virtualization, where each program would think that it owns a whole whole memory, but in fact it doesn't. Which means it creates some sort of abstraction, or this virtualization to enhance this ease of use, right? So the fundamental difference between demand paging versus swapping is, a demand paging is whenever you need the data, you fetch it in on-demand fashion. Whereas swapping is whenever there's a memory pressure, you need to swap something out. At the same time, you swap something in. So that swapping process needs some sort of decision making, which is the page replacement decision making under memory pressure. Okay, and this page replacement or cache replacement policy, we will be talking about in more detail in the next lecture. Okay, so again, under memory swapping, at the bottom of this slide, it shows a really simple example of how swapping looks like. In this example, at the top level, it shows the layout of the physical memory. And the bottom level, it shows the disk swap space. Let's assume it's a hard disk drive. Okay, HDD. And in this case, the swap space, which is part of the hard disk drive, is even larger in terms of capacity compared to that of a physical memory. And in this case, we are looking at 4 different processes. Process proc 0, proc 1, proc 2, and proc 3. Okay? As you can see, the first 3 processes, process 1, process 0, process 1, and process 2, they are within, so part of these 3 are within the physical memory. Okay? So as you can see, the first physical frame number 0 is occupied by a virtual page number 0 that belongs to process number 0. Okay, and the fourth physical frame number 3 is being occupied by the third process, which is process number 2. And again, the very first virtual page number of process number 2 occupy the last physical frame number. Okay. So the swap space, the part of disk space, it is solely reserved just for just as an extension of the physical memory, reserved for moving the pages back and forth between the physical memory and the disk. Okay, so this is what is this? The disk-based swap space is responsible for, and the operating system reads from or writes to the swap space at what granularity? At page size granularity. So it basically manages this particular swap space at this virtual page or physical frame granularity. If the size of the virtual page or the physical frame is 4 KB, it then manages this swap space at exactly the same granularity. Okay, and also in this example, as you can see, process number 3 is fully swapped out to disk because none of its virtual pages, none of its data is currently residing in the physical memory. So there's a dark colored process number 3, which is the fourth process. Okay, while the first 3 processes, process 0, process 1, and process 2, they have a part of it right now currently residing within the physical memory. So this slide, in this slide, we basically revisit this address translation protocol, address translation algorithms, but we are essentially looking at a slightly more advanced version with where it incorporates seg faults together with page faults. Okay, so let's go through this address translation, this improved address translation protocol, this more comprehensive version step by step, okay? So this is, first of all, this is from the hardware perspective. For each and every memory access or memory reference, it first the CPU tries to extract the virtual page number from the virtual address. And then the second step after that is to go ahead check the TLB, because the TLB is a translation local site buffer, which is responsible for caching the most recently accessed address translation information. So go ahead check TLB for that particular VPN of interest. If luckily there's a TLB hit, we end up with the fast path, right? So this is essentially a fast path. Why is a fast path? Because we could just directly fetch this corresponding physical address, the physical frame number, from the physical frame number field, and concatenate it with the offset to construct the physical address, and then use the physical address to access into the memory. So this is a fast path, right? And if unfortunately we have a TLB miss, which means the corresponding address translation information is not present within the TLB. So this is the slow path in terms of memory access, because we need to first fetch the corresponding page table entry, which is right now within memory, right? And then further check the valid bit of this particular page table entry. Recall that it has a valid bit, together it has a present bit, but we need to first check whether it's valid. If not, there's an exception, which is what? Which is essentially a seg fault. So the operating system will kick in and queue this process, okay? But if otherwise, it's valid, which is a good path, okay? So we move on to this step. We further check the other bit, which is a present bit. We check whether the present bit is 0 or 1. If it turns out to be 0, then we end up with another extremely slow path. There's another hardware, trap, which is an exception. So, which is essentially interrupt, okay? This is interrupt. Hardware interrupt. okay, which is essentially a page fault. It has to do with the page fault handler because this is a page miss, because the present bit is 0, meaning the virtual page, the physical, the data is not within the memory, but instead on disk, okay? If otherwise, the present bit is 1, okay? Then we end up with a relatively fast path. We just go ahead and extract the physical frame number, insert it into the populate the corresponding TLB entry, and then go ahead and retry. Okay? So the question is, which exact steps are expensive in this procedure? So it turns out these 4 different steps are expensive, but there are still different at different expensive level. For example, the very first, this process, this step, fetch the physical address from memory. So fetch the data from memory. So this is a memory access, which is relatively expensive, right? Which we've already learned this in the previous lecture. Okay, so this is another memory access, okay? Memory load. This is memory load. Okay, so this is relatively expensive. And this process, if the valid bit is 0, meaning it's invalid, this is way much more expensive compared to the memory load because the operating system will kick in and queue this process, which is kind of out of the scope of today's lecture. So let's just directly skip that. Okay, so moving on to this expensive step. So if it further check whether the present bit is 0 or 1. So if it turns out the present bit is 0, so it raises a hardware interrupt, which is a page fault interrupt. So it meaning there's a page fault, there's a page miss. So the operating system would go ahead, read something out from the disk I/O. So I will say this expensive step is way much more expensive compared to this to memory load because we're right now talking about disk I/O instead of memory memory read. Okay. So next, what exactly a page fault? So page fault is the act or the operation of accessing a page that is not currently within the physical memory. And this whole act is called a page fault. Okay, so operating system is involved or invoked to service this page fault in terms of a page fault interrupt. Okay, and the interrupt is handled by a handler, which is called the page fault handler. So again, as we've already seen like multiple times, this page table entry, it contains a corresponding information indicating the corresponding page address if this page happens to be residing on disk. Okay, the page address on disk. Okay, if the present bit is 0. Okay, so next, let's take a look at this protocol of page fault handler from the operating system perspective. This is something handled by operating system, okay? It has multiple steps. So here, this slide shows just a high-level pseudo algorithm, pseudo code, which is neatly defined. So first of all, as a very first step, it tries to locate a free page by looking at a free list. So the operating system maintains some free list data structure, which is a data structure that is used to track all the freely available physical frames within the memory. Okay, it tries to find a free page. It returns the corresponding, the very first encounter located physical frame number. And then it goes ahead and check whether this return value, this physical frame number is valid. If it's not valid, meaning it has a value of -1, okay? So we just enters into this if, branch. So within this if branch, it tries to do something which is, somehow expensive, which is evict page. We call that if the memory has already reached its capacity, we have, in order to bring something new into the memory, you have to make the eviction decision to first evict something out to make the room, right? So that requires to call this function, which is called evict page, and it returns the return value of this evict page function is the victim, the physical frame number of the victim. Okay, so this is another physical frame number. And then you enter into the next phase, which is a disk read, right? So this disk read function at a high level, it takes in two parameters. The first parameter is the interested page table entry, because it happens to be that this page table entry that has just been fetched, being accessed, it has a present bit of 0. So that it refers to its page table entry, this address field, okay? It tries to update this address with the second parameter, which is the physical frame number, which is the physical frame number of the victim that has just been swapped out to disk, okay? The victim, if any, okay? So there's a disk read, which is IO operation, which is extremely slow, obviously. And then followed by some, bookkeeping information, bookkeeping process. Try to update the metadata to try to flip the present bit of this page table entry from 0 to 1, okay? Meaning right now it's residing within the memory. And then update its corresponding physical frame number field to reflect the current location, which is a physical frame number within the memory. And then resume or retry the instruction. So the question is, which exact steps are expensive or relatively more expensive? So the answer is, so for sure, this step is the most expensive step because it incurs disk IO, right? As we've already discussed, IO operation. So another step which is ahead of it is this evict page operation. Its expensiveness, it depends, right? Why it depends? It's because this evict page operation, it might incur IO or might not incur IO. So when does it incur IO operation? It's because if the data that you want to evict out, you need to save it, save the state. The state is precious. You need to memorize the state. So you need to faithfully evict it out to disk. So in the worst case, if you have to memorize the state, there's an IO operation. But the best case is, if you happen to locate some data that turns out to be a garbage or some, orphan data that is useless, you could just completely evict it. You could just completely erase it, remove it without sending it to the backing store. So there's no IO in this case. Okay, so maybe that page, the data that is backed within the page that you try to evict out, belongs to some process that has already gone, right? So there's no IO, just simply erase it. So that is why this process, this particular step depends, okay? So within each one of these two different operations, you have to make the decision, right? So with respect to what victim that you want to pick to evict, right? There's some policy you need to follow. And the second operation, what to read, right? So this is deterministic because it's already specified, okay? But these are two questions that needs to be resolved at runtime by the operating system. And in this slide, it shows the major steps at a high level from the hardware perspective. Okay, if you take a look at the very first step, so you try to load some, perform some memory reference, right? So there's virtual memory access. You try to load the memory, which is called M, right? So you first refer to the page table, and it turns out this I bit, or let's say this is P bit, present bit, is 0. So that means there's a trap, there's a hardware interrupt trap that traps into operating system. So right now, operating system gains full control. Okay, and then operating system starts looking for the requested page from the backing store. In this case, this backing store is hard disk drive or disk. Okay, and it spends some time, maybe like 20 milliseconds. And after 20 milliseconds, it successfully locates this data of interest. And then as the next step, it tries to bring the data into the memory. Okay, so it first locates there's a free frame so that it could bring this on-disk data into this free frame within the physical memory. And then as the next step, you need to reset the page table or update the corresponding page table entry so that right now it points to this physical frame number, okay, which is exactly this this frame number. And then retry the instruction as the next step or restart the instruction. So this basically covers again in animation or visualization how the page fault protocol works. So let's next talk about the performance impact of page faults. Because page faults incur I/O operations, so the page fault operation is extremely expensive. So that would impact the system performance negatively or badly, right? Because the process which is currently experiencing the page fault will be completely stalled, right? Until the missing page is brought into the main memory. So because it's being blocked, it's waiting for the I/O to be fully serviced. Operating system would move this particular waiting process into the waiting state. So that is waiting for this particular I/O event to be fully serviced, to be successfully serviced. Okay? And more importantly, again, dealing with page fault always involves disk I/Os. It, at the same time, increases the demand to the disk drive, which is extremely slow, which is a bottleneck of the performance. And at the same time, it impacts the waiting time dramatically to the process. So that is why for an operating system with extremely small, for a system with extremely small main memory, its performance is basically bottlenecked by the disk I/O. So the user would experience like intermittent or frequent freezing when he or she is operating on that, controlling that application, using that application, okay? So another concept is because the physical memory capacity is always, there's a cap, hard cap. The physical memory capacity is limited. So the operating system would always use the physical memory as some sort, as a cache, right? So at the same time, we want to improve the level of multi-programming by bringing in and co-locating multiple programs, multiple processes within the memory at the same time. But this would increase the memory pressure, right? So at a certain point of time, the memory is reaching its full capacity, and then operating system will kick in to try to make the decision with regard to which page, which memory block to be evicted out so that the operating system could bring in new process, new data, okay? So this way, the operating system use memory as some kind of, memory cache. And the whole process to to pick a process as victim and completely replace it with a new page. And this whole process is called page replacement process. And the policy that guides the page replacement process is called page replacement policy or page replacement algorithm, which is a core topic that we will be discussing in the next lecture. Okay, so a little bit more about memory as a cache. So under the hood, operating system maintains these two different thresholds, right? So it maintains a high watermark, and at the same time, it maintains a low watermark. So whenever the operating system notice free memory is below this so-called low watermark, it indicates that there's a memory pressure. So the operating system, there's a background operating system thread, which is called swap or page daemon, which kicks in and start running in the background to constantly freeing memory, to constantly try to swapping data out from a memory data out to the disk. It tries to evict the page until there are high watermark worth of memory space available. Okay, so this is essentially a heuristic. It uses this two threshold to guide the heuristic, to guide the starting and stopping termination of this eviction process. Okay.